Sure. Yeah. Good luck. Yeah, sounds good. 2 minutes. 2 minutes. Yep. All right. It's 11. We're going to get started. Lord, thank you so much for bringing us together this morning. Thank you for all the blessings that you've given us. Pray that you would help us to stay focused for the next few hours. Help us to just be aware of what we're trying to accomplish. Help us to stay in the game and to keep ourselves motivated for the remainder of our time this summer. In your name we pray. Amen. All right. Guys, I am gonna be honest with you, I did not feel like waking up this morning. It was a tough one for me to get out of bed. Just didn't feel like doing it. I had to drop my mother-in-law off at the airport last night because she decided to take an 11:30 flight, which was great. And I enjoy being able to help folks. And I love that she was able to come for Mother's Day. That was also great. But that's just a late night. I'm old. I told you guys, I'm old. And being up past 9 o'clock is a real struggle for me. Anyway, enough about me. That's true. Thank you, Dave. Thank you. All right. So what are we doing today? We'll recap a little bit. We're going to continue talking about moments. All right. It's all about moments. And then we're going to talk about how do we use all the things that we've learned to this point to be able to simplify systems of forces applied to a particle. Right. Okay, cool. So, balloon. I'm gonna be honest, I'm a little bit confused about that too. Oh, the balloon problem. I already forgot about it. Yeah, no. The balloon problem. That's right, the hot air balloon. Yeah, it's a problem that we did with vectors. It's the problem that we did with vectors. The big takeaway there is what? What was the big takeaway of the balloon problem? Unit vectors. Don't be afraid of unit vectors. And in fact, if the only information that you have is distances, you are probably being guided towards unit vectors. Now, this is just a comment on test taking 101, right? When you read the problems that you are given here in college for exams, right? And when you take other exams, like if you take the FE, the Fundamentals of Engineering exam, right, or the PE, and even when you took other standardized tests before you got here, right? The first thing you need to do is understand what you're being asked, right? And it sounds trivial, right? But the next thing you need to do is, okay, now that I know what I'm being asked for, what information was I given and what can I do with it, right? So in this problem, we were asked for the force P, right? But we also understood that when we're given only one other force, we probably need to figure out what the other two are that we're missing. What information were we given? We were given one force magnitude and a bunch of distances. In that case, whenever you guys are given nothing but distances, and you know that your forces are acting on cables, right, or lines or ropes or anything that is between 2 points, you know the force has to travel through that thing, right? And that's just an living in the world, right? If I'm going to pick up this chair, right, I need to have enough force more than the weight of the chair to pick it up. If I'm going to push it somewhere, all of the force that I'm using to push it gets transmitted through the rest of this chair down to the wheels, right? If I'm pushing at an angle, it's going into the ground. Force travels through medium that's how it is. And in the case of that balloon, those lines that we had holding it to, we know forces have to travel through there. And if you know that you have two systems of vectors that live in the same space, then the unit vector has to be the same. Another way of thinking about it is this. Another way of thinking about it is this. If I have an angle, right, say I'm pointing out at 45 degrees, right? Anything that is on that line, no matter what it is, this imaginary line, it's still 45 degrees from my position, right? It doesn't change. Same thing with these four, but we weren't given angles, and you don't need them because we have the unit vectors. Because the unit vectors have implicit information about angle coded within them, okay? But remember, if you're given, you don't need angles if they're not given to you, if you have all the distances. If you have a combination of distances and angles, you're probably going to need both trig and unit vectors, right? So be aware. The other thing that I want to get to is all of the problems that you are ever asked to solve in an academic setting do have a prescribed solution, right? So you need to understand that no matter what your gut reaction might be, and I've been there too, like I don't have enough information to solve this problem. But you do. I promise you. I promise you that you do. Okay. But that's the big thing with the balloon problem, right? Is recognizing that unit vectors might be the way that we need to do it, right? And I would argue much easier than doing like a double projection conceptually, right? Like where you have to project down to the z-axis and then down to the xy plane, and then you end up having to use 3 different trig functions and 2 different angles to figure out what your angle is, and there you go. Culver is both the last name of Sam, but also an ice cream and burger place. There you go, nailed it. You're up there, man. You made it. Somebody doesn't understand Sam. Whoever that is, you take that up with Sam after class. Cross product. Cross product's a big deal. All right, we do a lot of things with cross products in this class, and vectors in general, right? And what is the big deal with cross products? The biggest deal about cross products is that if I have 2 vectors, I can create a third vector that is 90 degrees to both of those vectors by taking the cross product of the 2. The direction in which that vector points matters depending on the order that I take the cross product in, right? So we talked about this. P cross Q is not the same as Q cross. They would be the negative of each other. Why? Because of the right-hand rule. Right? Right-hand rule is the king when it comes to determining the sense of vectors that we're taking the cross product of. If you're talking about actually doing a cross product, there's a couple of different ways that you can do it, right? You can write down the vectors and then you can distribute all the different cross products out, which is fine. You can do it in the determinant style, which is the graphical way that I like to do them, where you write ijk on the top, and you have your 2 vectors underneath, cover up the I column and the j, I column and the top, and you're left with the 4 numbers, cross multiply, subtract, cross multiply. You do rinse and repeat as you go through. But in that case, you need to make sure that you're getting the sum correct, right? And a lot of this comes down to, technically speaking, taking a cross product is, can we multiply and subtract things correctly, right? It's not, the math isn't hard. We're not asking you to do any calc, right? This is arithmetic that's ruling the day here. Torque everything. Sure. Okay. I think that might be 2 things. Nothing. I think it seemed like balloon problem and cross products are the biggest offenders from yesterday. I would recommend that if you don't feel comfortable with the balloon problem, I would recommend trying it again on your own, right? Step through it and see if it makes sense, right? Try to, whenever you're doing that, don't use try to stay away from the solutions unless you get absolutely stuck, right? There's other problems in the book that use 3-dimensional, like if you go to chapter 3, In the textbook, there's a ton of problems in there that have 3D vectors. You can practice your angles, you can practice you can practice the whole thing. The last class I also said I had some review problems. We didn't get to them. So what I'm going to do is I am going to post those in the announcements in class in Halo. Okay. And then you guys can, what I'll probably do is I will probably gather some more because those are all chapter one. So essentially I'm going to provide a review, some review problems for you guys for the quiz, even though I said I wasn't going to, but I think we're going to have timing to cover them. So I'm going to give you guys a review guide, basically. It'll have a few problems from chapters 1, 2, and 3, which is what the stuff for the quiz is going to be on. Okay. I'll post those by the end of the week in Halo in the announcements. And I will propose, I will put solutions up the following week. Okay. So you guys will have full solutions worked out on the whole thing. All right. Okay. All right. Did I miss any other things that are really bugging folks that is there anything that's really I need to address right now? It's immediate. Anything that wasn't covered right then? Are you guys feeling okay? Ish. I know it's like drinking from a fire hose, Dave. Yeah, because you can't request the answer to the problem. Yeah. No, so I know some folks have had issues with that. I don't know what the deal is. I think if you go through the entire homework, you should be able to get another attempt at that problem later. But the way that the settings are set up is that it won't release the full answer to any problem until after the due date. Sure. No, I get it. I don't know what like I don't know on the Pearson side what the deal is with that. So yeah, my suggestion would be if you get down to that point, don't hit the request answer button. I would say your time would be better spent sending me a message and asking me a question, and we can have a discussion about it. All right, let's do a problem. This one looks fun, right? Super fun. What? No. Well, what the heck is this thing? It's like it's all bendy and stuff. I don't know. It doesn't tell us what it is. It just says you're given the force in the geometry shown. So I've got this cool. I don't know. This is let's get crazy with this. Is some playground equipment. I'll just say it looks like something would be on a playground. And what's intended is that the kids are going to hang from this part and swing around because that's what kids like to do. It's their favorite. You could put anything up and they'll climb on it. They're like cats. All right. Anyway, I've got this force that's coming off of point C. But what I want to know is the moment of that force about point A at the wall. Okay. So first of all, why? Why do I care about the moment about this is connected to the wall? Why would I care? Exactly. Because it gets fastened to the wall, and if the moment is too strong, you rip it out of the wall. Let me tell you this story. Before we moved into our current house, we were staying in an Airbnb for a couple of weeks. And my youngest son got out of the shower there and decided that he was going to hang on the towel rack. That didn't work out so well because the moment that he generated was too large for the drywall and it ripped a large chunk out of that drywall, and I had to do a drywall replacement in a house that we were renting. So that's the real world application of why moments matter. Okay. because then you have to go to Home Depot and spend between $20 and $100, depending on how big the hole is, to fix that up. So yeah, yeah. 7, at least 7. At least 7. All right. So how do we do this problem, right? Well, okay. Question. What is the definition of a moment? Yeah. Except the other way. Yes. R cross F. Because remember, the direction matters, right? The direction matters. So what do we know? Let's write down what we know first, right? Well, it's already they told us that we were given the force in the geometry, but the magnitude of this force is 80 Newton, right? And we're told a bunch of angles that I'm not going to rewrite here. But we do know distances and angles, right? So I'll remind myself that we've got distances and angles. And my unknown here is the moment at A. A moment at A. And that's the typical convention, right? The moment about A. The moment about a point. Remember, a moment is always about a point. It is not at a point, right? It's always happening about it. Great. Okay, so as Kenton let us know, we typically say that that's our moment. I'm going to call this RA. We'll call it RA. You can call it RAC if you want, because technically, remember, this is from, let's try that again. Remember that this is R, is always directed from the point we are interested in taking the moment about to a point on the line of action of that force. So technically, we could put it here. We could put it back here. Heck, we could probably put it here somewhere, right? If this force, since its line of action is there, right? One of these makes a lot of sense. The others don't, right? The one that goes to the point where we have all the measurements to it, that makes sense for us to take that vector, because otherwise you don't know what these other options are, right? But, you know, by definition, it could be any of those things. Okay, so here's R. And we know that that's RA or RAC, whatever we're calling it. All right. All right. So let's write down what RA is. And we'll do that here. So somebody help me out. What's the I component for RA? 550 what? No. Is everybody in agreement that that is what it would be? Yeah, I'm getting some nods. Yeah, sure. 550 I. Do you see that, right? Because if I wanted to go from A to C in the X direction, I need to go 300 millimeters plus another 250 millimeters, right? This whole distance from here to here, right? That makes sense? Yeah, maybe. Stop asking questions. It's 11 a.m. How dare you? Sorry. I know that you guys are probably used to going to bed well past 9 o'clock. Okay. Back when I was in college, I thought sleep was for fools. And now I wish I had that sleep back. Okay. J direction. How far do I need to go? K direction. And we said that these are all in millimeters. Now, It is a valid unit to say that a torque is in a Newton millimeter, right? But some people are purists and would prefer that it be a Newton meter, right? So this question didn't really ask us for specific units, but again, when you're doing homework, make sure that you're fulfilling the units that they are expecting to see, not the units that you want. The funny thing about a Newton millimeter is that it is actually the same as a millinewton meter. Think about that one. Sometimes it makes sense to talk about it in Newton millimeters, right? It does, and that's a fact. Research that I did back in my PhD, we reported all torques that were seen on the human hand in Newton millimeters, right? Why? Because millimeter scale of movement was what we were looking at. And so it wouldn't have made sense to quantify it as a Newton meter. In this case, since everything's giving in millimeters, I think it would probably make sense to leave it in millimeters, but I know that the book probably has its own ideas, right? So just for completeness, we will convert this to meters, right? Just for funsies. And now I think we don't need this picture anymore. So I'll move these things up. Okay, cool. That was a lie. We do need that picture. I forgot. What's the other thing that we need if we're going to define the moment? The force vector. So let's do that. That one looks fun, right? Yeah, absolutely. What do we know about it? Well, we know that the magnitude is 80. Right? So if I want the x direction component of this force, how am I going to do that? All right. Let's start with an easy one. If I wanted the k direction component of this force, how would I do the k direction component of this force? So let me show you what I'm talking about. This force breaks down into the z direction, right? When we have the z direction there, the other component is here. Yeah. So that first triangle that we're looking at, what do we have? This first triangle. This is a right triangle. We know it's a right triangle because before I covered it up, they have the nice square in the corner there, letting you know that that's 90-degree angle, right? It doesn't look like it's a 90-degree angle, but that's because you're wonky at it. If you turned it and looked at it straight on, you'd be like, that's great. Great. So now I've got these two vectors. This one is clearly my z component, right? This one is somewhere in the xy plane, right? So it breaks down into a second triangle. Which gives us this second triangle. And those are our x and our y components, right? So this is the double projection that we were talking about earlier. So if I want the x direction component, right? I want this component. Well, if I was just worried about this angle, right, what would that be? It'd be sine of 40 degrees, right? But in order for me to take the original vector up, I need the orange vector, right? How do I get that up there? Yeah, so it should be 80 times the cosine of 30 degrees. Oh, no, that's an arrow. That's not a, hold on. I can't write this in arrows, apparently. 80 times the cosine of 30 degrees times the sine of 40 degrees. So I'm going to go back and we're talking about this again one more time because I want to make sure everybody is crystal on this idea because I know it's confusing. We start here. In order for me to bring this up to the orange vector, the orange vector is what? That is 80 times cosine of 30, right? But this vector has two components in the x and the y direction. In order for me to back that out, I now have this vector, right? So let me highlight it here. No, that was the wrong color. We've got this one, right? That is our orange vector. That's the orange vector. Then if I take the sine of 40 of this vector, right? That gives me the x component, okay? What if I want the y component? Right, yes. So 80 cosine 30 again. Remember, because it needs to be the orange vector first. And now we just want the opposite component. And then we already said it, but in the z direction, sorry, this is going to be 80 times the sine of 30 degrees because we're looking for the pink vector there. Right? That's the pink vector. Z component. I probably should have used different colors up here, but 6 of one, half dozen of the other. We're in too deep to switch those colors now. Draw over them with a different color? I could, but I could do that for sure. Okay, does that make sense? Is everybody tracking there? Another way that people sometimes will notate this is they'll rename this orange vector something like FH or just whatever random variable, right? And they'll say, well, this gets me FH, so this is FH times the sine of 40 degrees, right? Because it's just another vector we are resolving into components. If this was dimensional, we would do this, another time, and you would keep stacking trig functions. Well, we won't do 4-dimensional. It does make sense. The stately tetrahedron. Anyway, questions on that in particular? Yeah. Other. Sure, because we're using this angle here, which goes from, so if you were to look at it from the side, right, you end up with this orange vector here, this pink vector here, and here's our original force vector, right? And this angle is our 30 degrees, right? And so in order to get the k component, that's why it would be sine of 30. Make sense? Yeah. Yeah. It's sometimes looking at angles in 3D, I know it can get cluttered and messy, which is yet another reason why having the distances is really helpful, right? Because it's typically easier to read distances off of a 3-dimensional drawing. Just really make sure that you're understanding where those arrows are pointing us, okay? And what's between what. Cool. Yeah, cool. Yes. So if we had information, because that's clear, it looks like there's some cable tied up here, right? I joked that it's playground equipment. I don't know. I don't know what they gave us zero context on this. They gave us zero context on this, right? So I really don't know. But if we had been given some information here about where point C terminates compared to point A, then, or compared to the end there, right? We could have come up with a unit vector from C down here that's in line with F, yeah? And in that case, then you would use unit vectors. But in this case, because it's not projecting onto anything that we know, we have to bring it back to Cartesian itself. All right, does that make sense? So this is an instance where let the information that we're given direct how we're gonna kind of do this problem, right? Like I wouldn't tell you to make a unit vector here because we have all of the angles that we need to break this down, right? Any other questions on this? Obviously, we're just going to leave these sines and cosines as they are because everybody loves to work in sines and cosines, so there's no problem. But instead, let's just do the math out really quick. So this ends up being 44. I'm going to use one decimal just for reporting, but I would use them all for my calcs, right? I plus 53.1J minus 40 in the K. And this is all going to be Newton. I probably should have put Newton back here too. All right. Now we're done with the drawing for sure. So now we do this. Right, and this is probably important. There's multiple boxes around it now. I want to make sure that if you don't have this in your notebook at the time, that it's in your notebook now. This is important. If you're curious, I'm referring to this particular equation. Moment is R cross F. This one here. That one. There. Okay. Cool. So we're gonna use that equation. So let's set it up and let's make the pen this thickness. So the moment of about A is equal to our position vector from A to our force times our force vector, right? Or cross our force vector, excuse me, which is this beautiful cross product here with our IJK, 0.55, 0.4, and negative 0.2, because then I don't have to worry about multiplying seemingly large numbers, right? And our force vector, which is 44.5, 53.1, and negative 40. Okay. Okay. So let's do this visually. Do that. So the first one that I'm going to do is I'm going to cover those, well, too much. We're going to cover this row and column to start, right? But before we go ahead and do that, let me, well, do it this way. Let me write down my IJK circle, because that's always a fun time. IJK. Just to remind myself of the directionality of the cross product. So back to it. If we're going to do the first one, we cover up the ith column and the top row, and we're left with this. So if I'm going to do my cross product, right, well, I would have 0.4 times negative 40 minus 53.1 times negative 0.2. So we'll write that down. 0.4 times negative 40 minus 53.1 times negative 0.2. And that's all going to be in the, well, it is the J column and the K column. So J cross K, looking at my IJK circle right here. So J cross K is in the positive direction, so that should give me a positive I. These are my I components. Great. Then we'll keep the top covered, but we'll slide over and cover up the J column. Okay. Now what? 0.55 times negative 40 minus 44.5 times negative 0.2. Okay. Going back to my circle up here. This is I and K columns, right? I cross K. Oh, that pushes the circle in the opposite direction. That's going to give us a negative J. So I'll put my negative out here, J. Last one. I cover up the K column, 0.55 times 53.1 minus 44.5 times 0.4. Okay. No. Okay, go back to the IJK circle. This one is I and J. I cross J, positive K. Plus. All right. Now we just add them up. Multiply, subtract, add, do the arithmetic, right? So we find out that MA is equal to, well, if I do this first one here, right, I'll get negative 5.38 in the I, about the I, plus 13.1 around the J, plus 11.4 in the K, Newton meters. And some people put that dot in between there to signify that you're multiplying newtons and meters. There it is. So what's important about this result? Well, first off, applying a force in 3 dimensions can cause a rotation in about 3 axes. The other thing I want you to notice is that this is not intuitive in any way, shape, or form. If I were to ask you what was your gut feeling about the different rotations about the different axes here, you would have been like, sorry. And I don't disagree with that. I don't think that this is intuitive at all to look at this and be, if you can look at this and be like, yeah, for sure, that was going to be a negative, that's going to be a clockwise rotation around the x-axis. Good for you. Like let's go to Vegas. I got, but my brain doesn't work that way. Okay. Um, do the math. Do the math. It'll tell if you track your vectors correct. If you bookkeep your vectors correctly, it'll tell you everything you need to know. Could we have broken this down and done the scalar method, right? Could we? Maybe. I mean, it's a pretty big ask. I mean, we have the X, Y, and Z components. You would just have to figure out exact perpendicular distances to A in all those cases, which you could probably do, right? I think that this is much quicker since I just have to write down two vectors and do a cross product. But if you want to try it the scalar way, you can give it a shot. I haven't done it that way. I don't know. I'm curious. You guys have any questions about this? Cross products, whether or not you should write down this formula. And I say formula, it's pretty basic equation. Well, everyone's all right. Are we okay with this? Let's move on. Stop talking to us about this thing. All right, fine. Cool. All right. So stuff that's due. You guys got homework due on Thursday by midnight. Product plan is due on Sunday. Quiz a week from Thursday, then another homework due, then another homework, and then quiz 2. And then once we clear quiz 1, once we clear Sunday, I'll put 2 more assignments on there because if I put more than this many, it starts to get really small and it's not helpful. Also, I would pretty much guarantee that none of you really care beyond quiz 1 what's actually happening at this point. I would guess. All right. Questions about things that are due? Okay, I would do those things for sure. 100%. Remember it, like Michael Scott says, okay, you can't win if you don't play, but you also can't play if you don't win. Okay. All right, this is one that I say all the time. I've said it multiple times in this class already. They are my isms, which means they are things that I say like all the time. Answer the question that is asked before you answer the question that isn't asked, right? Okay, what does that mean? It means that if I ask you for something very specific, make sure you answer that thing. If I don't ask you, for instance, if I say solve for the resultant vector using the triangle method, if you don't use the triangle method, you haven't answered the question. It's great that you can do it the other way. Frankly, no one's going to ask you to do the triangle method. But there's the thing, right? If I ask you whatever you were asked for, do that thing first and then add to it, right? Key to life. Do the work that you're asked to do, and then if you want to add more and you have time to add more, then you add more. But always start with the base. Okay. Let's talk about, last class we talked about moments about a point, right? But we are going to extend what we just learned to moving that around an axis, right? But before we get there, a triple scalar product, that's weird, U dot R cross F results in what? A scalar quantity, a vector quantity, 0, a unit vector, or an imaginary number. Triple scalar product. Yeah, use them whiteboards. Don't be shy. Don't let the people around you see your answers. That's cheating. Come up with your own answers. There's only 5 choices. I mean, it's not as good as the SATs, but pretty close. 20%. When you're done, pop them up. U is a vector. It could be a unit vector, could not be a unit vector. It's any vector. It's every man's vector. It's a working class vector. Blue collar vector. All right. All right. There's a wide variety. There's a wide variety in here. Yeah, we got some B's, we got some E, we got some D's, A's, B's. All right. All right. So keep them up, keep them up. See, I'm gonna figure out a way to do this electronically one day. That'd be great. All right. Oh, sorry. No answer. Nobody knows. Uh, no, but for real. So let's take a look at it, right? What is the triple scalar product? Well, all right, first of all, it's in the name, right? But secondly, let's look at this. What is the order of operations? You do the cross product first, right? Because it's in the parentheses. And then you're taking the dot product of two vectors. So the dot product of two vectors should give us a scalar. So the answer is A. Answer is A. Right? Answer is A. Yeah. Oh man. All right. So the answer is A. Also, it's called a triple scalar product. It probably gives us a scalar. Right. Here's an interesting thing about a triple scalar product, right? Let's think about what we know about cross products and dot products, right? When you take the cross product, you create a vector that is 90 degrees to those two things, right? In this case, we've got a moment. You have some moment, right? When you take the dot product, you're projecting that vector onto a different axis, right? So this allows us to take two different vectors or three different vectors, create a brand new vector that's 90 degrees to two of them, and then project something else on there. So we can actually project our moment on an axis of our interest. And again, I haven't said why, right? You're like, well, that sounds great, Dr. D. Never going to have to do that. Nobody, never, ever. All right, well, why should you care? Because everybody uses ratchets all the time. It's one of I would argue that ratchet is a must-have tool, and if you do not have one in your garage or wherever you keep your tools, a basement, probably not in Arizona, but wherever. Attic, it's again not in Arizona. Don't put anything in your attic. No, definitely not kids. Also not Christmas decorations. I have a lot of friends who melt their Christmas decorations by keeping them up there. Anyway, when I have a force P and I'm creating a moment around point A, right? Does all of that moment act to turn the socket? And how could I calculate that? Well, yeah, sure, you can do that. I mean, no one's probably, when you're at home, no one's going to be like, hey, tell me how much torque you need to remove this bolt from your kid's bicycle, right? Or this piece of furniture that nobody wants in your house anymore, right? All that stuff. Or, hey, how much do I need to take apart this shed that you put up during COVID, but now that COVID's over, nobody wants the shed anymore, so it's gone, right? Anyway, not that that happened to anyone that I know. So is all of this going? No, not all of it. Some of this force is going to be off axis, right? And if we took but we want to know how much of it is actually being applied about this axis, right? All right. What about this? Sleeve A of this bracket can provide a maximum resisting moment of 125 Newton meter, excuse me. About the x-axis, how would you determine the magnitude of the force before turning the x-axis occurs? That's a really complicated problem that involves us understanding frictional moments that we're not going to answer today specifically, but might at the end of the semester when we're talking about friction, because it turns out that friction is the last topic that we will talk about, because that leads directly into dynamics for some of you. Anyway, but how can we figure out how much force we need before we overcome friction, right? Again, well, if we know what the maximum moment is, we can probably figure out the cross product, right? Or solve it. Before we get into this, another really good example of this is when you open a door, okay, where are you creating a moment about? The hinge. So you don't care typically what the moment is around the center of the door. You care about where it is rotating around, right? And so in this case, right, we would want to project our force and create a moment around the hinge, which is a different axis than our center of gravity. But anyway, we'll start with the scalar version of this, right? So hopefully you remember from yesterday that the scalar version of a moment is just the force times the distance that we are away perpendicular from the point that we're interested around. In this case, we're using O, and O is weird one to choose because people like to associate that with the origin, but what we're really saying is this is anywhere. Wherever you choose the origin to be, that's where we're taking the moment about, okay? So the moment about O is equal to the force that's applied multiplied by its distance away perpendicularly from point O. And we talked about that yesterday with that L problem that we did. Given that DO is perpendicular to the force's line of action, right? So can we extend this and say, instead of that being about a point, can we extend this to say, okay, well, I know that everything is rotating about a specific axis, right? And the answer is, yeah, we can do that. All right, so in this figure, the moment about the y-axis would be the moment in the y is equal to the force in the z times the distance away from that axis, the y-axis, in the x direction. Unless the force and the distance can be easily resolved into components, these calculations can be pretty difficult, right, if you do this. So what do we do? Because we don't want to make things more difficult. Things are already difficult, right? Eggs cost a lot of money. Milk's expensive, right? Well, make moments great again, guys. So seriously, what we do? Well, we can move O, right? So one of the things that you'll see me do a lot when we get really into solving equations with moments is you can take the moment about any point that you want, okay? So it makes the most sense to take the moment around the point that has the most forces that pass through it. Why? No. Well, yeah, but what's the definition of a moment? Force times the distance. If I'm taking the moment at a point that has a lot of forces that pass through it, what's that distance? 0, which means it doesn't provide a moment. So I can zero out a lot of these things, right, and simplify the problem tremendously, right? So here's my force, right? I want the moment about this bolt, right? If this is purely perpendicular, that's great, right? I can just do this and be done with it. I don't need to worry about any of my off-axis components, right? If I use this y-axis here, right, it's just projecting that distance of there. You can also change your coordinate system. If you didn't use Cartesian and use like a radial coordinate system, that actually helps with this particular type of problem, but we're not going to worry about that. All right, vectors. Vectors have the answer because they always have the answer because vectors are the best. And this whole class is secretly about vectors, even though I told you up front that it's about vectors, but nobody believed me. But we're traditionally almost We're almost 8 lectures in what a normal semester would be, and I haven't done anything except talk to you about vectors and unit conversion. And so you're all like, man, this was what's going on here, right? Anyway, so our goal is to find the moment of F, the tendency to rotate about a body, about the A axis here, right? So I have this deflated balloon thing here, right? Because reasons. And I have this point O, and here's my axis R, or my axis U of A, right? And I want to find what's the moment around this axis from A to A. I'm going to project my moment around here. Okay, so first we have to figure out what the moment is. You can't project it if you don't know what it is, right? And so we do R cross F, right? We bookkeep our vectors, right? We do our good cross product. And then we do a dot product between this axis and the moment that we just found. And this is a triple scalar product, right? What we were just talking about. Because what it does is it takes this moment and it projects the components of it along the axis that we are interested in, right? So to belabor the point, here's so essentially, notice how the top here has changed. You can do a triple scalar product represented in a determinant as well. Because why did I, j, and k change in this case? What's that, Tyler? Right, exactly. Because we are projecting this on that axis, we want the components of I, j, and k in the A, along the A axis, right? So that's that new vector. So instead of having I, j, k, you'll just have that new vector there. But what you'll see is if you leave it symbolic for that portion, you'll have, I don't know, let's say ry times fz minus fy times rz times uax, right? And you do that all together, you'll get a vector dot another vector, portion of a vector, right? And you can put those together. Right? So you can do it full out, or you can replace it up there. Either one is fine. Okay. 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 Here's a question. Concept check. Get your whiteboards. So if I have this vector operation, the quantity P cross Q dot R is equal to what? Is it P cross the quantity Q dot R? R dot the quantity P cross Q? P dot R cross Q dot R? P cross R dot Q cross R? We got some up. Is that an A or a B, Raf? You got the oh, it's not on there. Ah, failed again. It's B. It's B. Why? Why is it B? Because a dot product is commutative, but a cross product is not. Right, we talked about that last class. Okay. Remember, cross products are very specific about what order they have to be taken in, right? So P cross Q has to happen. P cross Q has to happen. But the dot product can be, because it ends in a scalar, it doesn't matter where we take the dot product on either side, okay? You can't take the dot product first, because then why? Because then you end up with two scalars, and then you can't take the cross product of scalars. That's not a thing. Cross product is purely, but you just do the multiplication, Dr. D. It's the x. That means multiplication. No. Okay. This American school system, all school systems, elementary school systems have been teaching it incorrectly. And frankly, I would like for you at the end of class to sign my petition to have that changed. I'll send it out, and actually I'll put it in the announcements. You guys can go to the link, have it, you know, We'll send it all the way to the top, all the way to Linda McMahon, the Department of Education. Okay. Okay. Concept check. The force F is acting along DC. Okay. Force F is acting along member DC here. All right. We're going to use a triple scalar to determine the moment of F about the bar BA. Okay. So this is acting down here. I know it doesn't look like it, but we're told this is acting right along DC, and we want the moment about this axis down here, about this bar. You could use any of the following position vectors for this, except for which one? So can we use R from B to C, R from A to D, R from A to C, R from D to B, or R from B to D? Which one is not acceptable of these if I was going to calculate the moment? Remember, we would use a triple scalar product, but that's not the question. The question is, if you had to do the R cross F part, which one of these 5 is not the guy that you can use? Which goes to tell you that all of them except one are usable. So which one is it? All right, what we got? We got? We got C's, C, C, E, D. All right. See, lots of C's coming up. You guys in the back, be proud of your answers. My answers are like my children. I love them all. Okay, D, C. No, not seeing some. Just throw it out there, guys. Throw it out there. See. Yeah. I've got an hour and a half. I can wait to see everybody's answer. All right. All right, so lots of C's, a couple D's. I don't think I saw any other letters. I'm gonna guess just right off the bat that this isn't gonna work. Yep. Okay. Great. All right. So which one is it? Before I answer that, what is so the definition of a moment is R cross F. Where it's the force vector and the position vector. What is the very specific condition for that position vector? So that's if it's scalar, it has to be perpendicular. Where does it have to go? Where does the position vector have to go between? All right, let's just say for a point, if I had a point and I was trying to get the position vector, what does that position vector have to be between? It's the position between the point that I'm interested in and what? What's the endpoint? I mean, yes, it's the endpoint, but that's not really, it's not like a Dharma Initiative lost thing. This is, I'm trying, like, the white lion. No. Okay. So yes, between the point and what? Between the point and what? What's that, David? Right, so that position vector has to go between the point and the force vector, right? Okay. But I said it a little bit more generally earlier. It needs to go between the point and any point along the force's line of action. What do we know about this force's line of action? It's anywhere along DC, right? As long as, if we wanted to make this infinitely long, it would be all the way along that, okay? And if we wanted the moment about this bar, instead of using the distance from a point, we're going to use the distance from this axis. Meaning that as long as we have a vector that goes from here to any point on DC, we have found the moment, right? The only one of these that doesn't go from BA to DC is this one, because it goes in the opposite direction. It goes from D to B. Okay. Okay. All of the rest of them you can find for all the rest of them. And on top of that, regardless for when you use, the moment should always be the right. It should. Well, that's not. It should be. Okay. Cool. Let's see how this actually works in practice, right? So I have this bracket. This is bracket, and I have a force that's F of 30 newtons, and it's angled up at that angle that has an alpha, a beta, and a gamma, and it's drawn really horribly, so you can't really see where beta is, but that's fine. We'll talk about it in a second. And they're 60, 60, and 45 degrees, respectively, for alpha, beta, and gamma. I'll note, please don't call them like fish, B, and weird Y. That's not their names. It's alpha, beta, and gamma. Okay. Yeah. What are we looking for? They were asked to find the moment of F about the A axis, the AA axis. Here's the AA axis. And hey, look, they told us that this is our R from O to A. That's great, right? Because our force is at A. Perfect. So we have a position vector already identified for us that goes from the axis of interest to point A, which is where our force is being applied. Great. And this is our unit vector for A. Right. Okay. Cool. So first things first, same thing we always do. Knowns and unknowns, if I can find the mouse here. Let's write down the knowns, the unknowns, right? So what do I know? F is 30 newtons, and we know alpha, beta, and gamma. I mean, they gave us really nice angles here too. Like, they're just really great. Let's talk about beta for a second, because it's hard to see from this picture. Beta is the angle between the y-axis and that force vector. So they've given us alpha, which is between the x-axis and the force vector, beta between the y-axis and the force vector, and gamma between the z-axis and the force vector. So they were really nice on this problem, and they gave us all of the angles without us having to do double projections, right? We know exactly what the angle is from the axis of interest. Yes. Mm-hmm. So in this textbook, they use that convention. It's pretty widely used. It's just random. No, the answer is no. Typically, when you're using Greek letters as variables like this, you would start with alpha, beta, gamma, and delta would be the next one and go through. Now, there are specific cases in other classes where like alpha later, when we talk about moments, alpha is going to signify angular acceleration. Um, you know, beta typically doesn't get used that much. Delta is obviously change, right? You'll see different ones used in other classes. There's a finite number of Greek letters, and so they get reused over and over. Fluid mechanics is going to be super fun. You get zeta. Zeta is for zeta is your damping ratio. Psi is your stream function. They're all over the place, and they're going to be different wherever you go. Uh, no, I would say no, unfortunately. I would say no. But typically, I mean, most people would go X, Y, Z, alpha, beta, gamma, right? Most people. But don't take that as, as gospel, so to speak. Hmm. We want to find the moment about A, which I'm going to write that way because that seemed like a good idea when I was doing this problem. We'll find out if that. You could also just, so here's the thing. If you wrote like the moment about A, like lowercase a, that's cool too. As long as you know where you're taking the moment about, right? Identify it. So what are the things that we need to do here, right? We've identified things that we know. We've identified that we want to find the moment about AA. Okay. So we were just got done talking about this, right? The moment about an axis is equal to the vector dot R cross F, right? That's, we are just talking about that. This seems like that would probably be a good thing to do here, right? Since we were specifically asked for the moment about this axis AA. Yeah. So we need to figure out things when we're looking at this equation, right? I know the magnitude of F and I have the directions, but I would need to come up with a vector, like a Cartesian for that, right? Cartesian or rectangular format, whatever you want to call it. Okay, so I want that in its I, J, K components. Cool. That seems pretty easy for us to do, right? We have good information on how to make that happen. R from O to A. Yeah, we can do that too. I have all the distances. That's great. Perfect. Right? Um, and then the unit vector from A. Okay. The unit vector of A. Okay. That's going to be interesting. We'll investigate that in a little bit, but I think we can handle it. The first three things we're going to do is define. Well, let's start with defining R, right? Why? Well, I mean, we need it, and I want to get rid of this picture in a second, so we're going to start with R so that I can just move the slide, right? And move the stuff so I can write things down. So R from O to A. All right, in the X direction, X is this way, in and out of the board, Z is positive up, and Y is kind of back into the board. So in the X direction, if I'm going from R, from O to A, how far do I need to go in the X direction? I heard negative 100. Yeah. Sorry, Ken. You had the magnitude correct, but the sign wrong. We're going back into the board, right? We're going this way. That's going to be in the I. What about in the J direction? Nothing. Nada? Zip? Zilch? It is. It's zero. That's interesting. We'll talk more about that in a minute. Very interesting. All right. Well, what about in the Z direction? And that's all in millimeters. So, because I am anti-millimeter, bring it right up to meters. Is everybody cool with me converting that directly to meters without going through the unit conversion? The answer should be yes. There was no multiple choice. Why would you say C to me? Anyway, such a dad joke. It's great. Dr. Jones would be so proud of me right now. All right, cool. We know the angles. I'm gonna remove this for a second because we know the angles. We're gonna go here. Oh, good. I left it up there. That was good foresight, on my opinion, on my position or whatever I'm trying to say. You guys fine. Yeah. All right. So we've got we need F and we need U. Let's do F first here. Okay. So if I want the X component of this force F, I want the X component of F. How do I get that? Thirty cosine alpha. Is everybody in agreement with that? 30 times cosine of alpha. Oh, nope. Mm-mm. Nope. There we go. All right. Let's write it this way for right now. I'm going to call it F times cosine alpha in the I. Okay, and I'm going to draw it in purple here. All right, so here's F. We want this. We're looking for that guy, right? So yeah, it's the adjacent side of that triangle with alpha. If you were to look at it from the side, right, you would get something that looked like that with F, and that would be your alpha angle. Okay. What about in the J direction? Right. Well, if you had the capital beta, then yes, but yeah, that's lowercase. You know what capital beta looks like? Yep, it's just this. There, it's capital beta. Nailed it. Here's your Greek lesson, Greek letter lessons with Dr. D. Like, share, subscribe. All right. What about in the Z direction? Weird why. All right, and just for illustrative purposes, make that one green. There. So you can see we have all of our components, right? And we have all the information we need to plug into that. So we'll just go ahead and do it. And this would be 30 cosine of 60 degrees. See, now you see why the book chose 60, right? Because that cosine of 60 is 1/2. Jackpot, man. It's like, look, if Hibbler, the genius who wrote this textbook, and multimillionaire who wrote every engineering textbook ever known to man, um, always pick 60 degrees, should be It should be or 30, right? Or 45. And look, it's even a gimme here because you're given 45 for the last one. So you can't possibly be right. The X and the Y are the same. You can't like it's perfect, right? Like it's so generous, so I mean, that's a great question. I have to think about that one. I think that might be one of those things where you'd get points, but probably not all the points. 'Cause there's a definite so like what's the point of the test supposed to be? Is it supposed to be busy work that I have you guys do for 2.5 hours, or is it supposed to be an assessment of things that you've learned? I feel like it's supposed to be an assessment of things that you've learned. Uh, well, it's assessment of things that you should have learned. Okay. All right. So we have F, and that's good because now we have everything we need to find our moment. We just need to find this U of A. U of A. So gross. Tucson, man. It's gross. All right. Anyway. Okay. Fine. All right. Anyway. How do we find U sub A? If I was going to write a vector for U sub A, what would it be? J? Who said? Why would it be J? It does look like the same direction as y-axis. Hey, let me ask you another question. What is the J component of ROA? 0, which would indicate to me that I didn't have to move in the J to create that vector, and so they should probably be the same, right? So U of A, U sub A, I'll write it up here, is just J in this case. It's just J. Well, that's lovely. That's really going to simplify a lot of things that we are about to do because we need to do a cross product and a dot product. Is your guys' lucky day because I know that you love both of those things so much, and now we have put them together in the triple scalar product. What's next? A quadruple vector product? No, it's not. Nothing. There's nothing left after that. All right, let's move these things around a little bit here. Yeah, no, this was I intended to do. It was my intent to make this the most difficult thing possible. Oh, yeah, perfect. Exactly. Try that one more time. There we go. I am going to get rid of a couple of these things. We don't need to know our knowns anymore. We've had those up there for a while. I'm going to take just the force vector here. Maybe. Come on. There we go. Take just the force vector. And just the position vector that we're using. Yeah, I know. I got it. I'm on it. It's a process, you know. -1 for Dr. D today. It's fine. Appreciate it. Thank you. Okay, sure. All right, so we're gonna do our triple product, right? Triple product. We want the moment about AA is, remember that's not a vector because it's a triple product, right? And a triple product doesn't give us a vector, it gives us a scalar. UA dot R A cross F. Okay, let's start with ROA cross F, which I'm going to call the moment about point O, because that's what it is. So moment about point O is equal to the cross product of ROA, negative 0.1, 0, 0.15, and F, which was 15, 15, 21.21. Okay. We do our cross product. I'll do it long form one more time for everybody. Put the black boxes in there. Okay. So in this case, we're going to get, oh, hey, we get 0 times 21.21 minus 15 times 0.15. Okay. Put my circle up here. That's I. That's, oh, sorry, that's J and K. Gives me positive I. We're good to go. Next one. Let's move our box over. Okay. Negative 0.1 times 21.21 minus 15 plus 0.15. Well, that is I into K, which if we go around would give us a negative J. And then the last one, we end up with negative 0.1 times 15 minus 0. And that's IJ positive K. So we're going to add it. So the moment about point O is equal to, when we crunch all of those things together, well, we're going to get, oh man, negative 15 times 0.15, negative 2.25i, negative 0.1 times 21.21, minus 15 times 0.15, plus 4.4 in the J, minus 1.5 in the K. Okay. I'm going to erase the cross product real quick. So we have a little bit more room to work. Move this guy like that. Okay. So we need UA dot this, right? So what is UA? UA we said was just J. J dot okay. What's J dot, well, 1J. Why not? I'm going to take the dot product. Okay. 1 times J dot negative 2.25i. What's J dot I? What's J dot J? What's J dot K? Hey, let's go. This is scalar. It does not tell us anything about the direction. So why is the direction drawn like that on this particular diagram? Hmm. Hmm. So let's think about it for a second, right? So if I have this axis, right, and this is a weird geometry. So I'm going to create this T-bar here, right, with two things. If I was to push up and around like this, it's kind of out of plane. So what is this actually saying, right? This is saying that we are not going to get any rotation about point A or about axis A that is out of the plane. And that's actually, it's not what it's saying, right? This is just saying how much of that rotation are we expecting to see around axis A from the moment that we've produced at point A, okay? Which is confusing that they used A and AA as the things. It sounds like I'm saying the same thing, okay? So in this case, why would it be a negative moment, right? Why wouldn't it be positive? The sense of the original moment, right, is if you were to take the magnitude, it has large portions, right? There's I and j components that would be counter, or that would be clockwise, and a j component that is counter. So I would argue that that is drawn incorrectly, is what I would argue. It should be a positive moment. It should be drawn counterclockwise, not clockwise. I think they were just trying to illustrate in this that, hey, there's a moment there. I don't think that I will tell you that from the triple scalar product, because it is a scalar, you cannot make a determination about the directionality of this moment based solely on the triple scalar product, okay? Because it is a scalar. But what if it had come out negative? Then it came out negative. Like it depends on it depends on a lot of different things. But in this case, right? Um, anyway, there you go. What's important about this is being able to project that moment down onto the axis. We understand what the overall moment is, and then we can make a determination later, not in this class, based off of material strengths and things like that, whether or not this will actually be a survivable moment that we can deal with, right? Are we going to bend this thing too much, right? Or is this thing free to spin? I mean, it's a hinge, right? It's a bracket. It looks like to me that it would be free to spin somewhat, probably not all the way. How much is it going to spin? All those things. But for today, that's all we needed. Yeah, so just to have a number there. That's it. There's no reason. 1 times j is j. Yeah. I can multiply anything by 1, can't I? I'm gonna freak you guys out real quick. Yeah, I mean, if the quantity was 0, I can multiply it by 1. Nothing would change. Too much? Sorry. Anyway, no. So yeah, if you were to put this into like MATLAB to do the triple scalar product, it would need the coefficient for the j, right? So you'd have to define a 0, 1, 0 vector to to do it against your moment vector. Okay, let's see. There's another one. They're in here. They're all over the place. They're all over the place. All right, there's 2 questions here. There's 2 questions here. Okay. First one, for finding the moment of the force F about the x-axis, the position vector in the triple scalar product should be RAC, RAB, RBA, or RBC. Okay. You're finding the force about the x-axis, or sorry, the moment about the x-axis. Which one is it? Is it A, RAC, RAB, RBA, or RBC? All right, so we just did the triple scalar product. You need to do R cross F. Which R do you need to find the original moment about point A? Mhm, mhm. What we got? Show me, show me. Some ABs, we got some BAs, ACs. Uh, ugh. Okay. All right, all right, all right. See, um, I'm afraid to hit the button, honestly. All right, so if we're looking at this, we want to find the thing in the triple scalar product. We need R cross F. All right, that means which R do we need? We need R from the x-axis down to the force. Which one of these gives us the distance from the x-axis down to our force at point B? Nope, that's going to be AB, RAB, right? Remember, we can go from any point on the x-axis down to any point on the force, right? We know the force is applied at B. We know that on the x-axis, we have A, right? From B to A is the opposite direction. It's going to give you not the correct moment. It's going to give you a negative, right? It's going to flip it. Okay. All right, the next part. Given R from 1 is 1I plus 2J meters, and the force is 10I plus 20J plus 30K Newton, what is the component of that moment about the y-axis? A, B, C, or D? Mhm, 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 mhm. Yeah. Come on, guys. Throw them up. We got B's, we got C's, lots of B's, a couple A's, couple A's. All right, so when you do these calcs out, what's going to be most important is what you get out of the J component of your moment, right? Because we know that the y-axis is defined as the J, so when we dot it, everything else will be 0 except for the J-axis. Oh, should give us what? Should give us minus 30, B. No, you just didn't do it completely. You didn't do the dot product. You found the moment about point A, or about wherever R is pointing you from, not what the magnitude is about the y-axis. All right, moment about an axis. That's great. Now let's talk about something that's really not, let's talk about something else. It's called the moment of a couple. Okay. Sometimes, yeah. Sometimes we'll have, what skills should we be determining here? We want to be able to define a couple and determine the moment of a couple, which is good because the name of this section of the slides is determine the moment of a couple. Okay, great. Here's a question. In statics, a couple is defined as what separated by a perpendicular distance? Two forces in the same direction, two forces of equal magnitude, two forces of equal magnitude acting in the same direction, and two forces of equal magnitude acting in opposite directions, A, B, C, or D. Well, this is thing because reading question, and if you didn't, and we don't really know, so you got a 25% chance here. Well, we were talking about moments and moments of a couple, so this has to have, probably do something with rotation, right? So I'm getting these and these, of course. It's D. D. Why is the answer? Because as we will find out, if I have two forces that are equal and opposite at the same distance away from the center of rotation, that's how I cause a rotation, right? And so I can take those two forces that are equal yet oppositely directed, and I can combine them into the net effect of just being a moment on that object. Okay. Okay, another one. The moment of a couple is called a free, spinning, fixed, or sliding vector. There's only really two answers that make sense from a from vector terminology standpoint. Free, spinning, fixed, or sliding. Yes. Uh-huh. Oh, sorry. We got C's, we got B's, we got D's, we got A. Okay. We got going. So let's talk about each of these individually. A free vector, that means I can put it wherever I want. That's not the case, right? I can't just put, well, there are certain cases where this can be a free vector, right? But typically it's not, because depending on where I put the forces, that's going to depend where the moment is, right? But if it's just about an axis, then yes, I can put it wherever I want along that axis, right? Okay, spinning. A spinning vector isn't a thing. That is not a thing. But the torque, the moment you said that the thing is not a spinning vector. We don't talk about spinning vectors. Fixed vector, yes, sometimes this is a fixed vector if it's about a point. If it's about an axis, it's not a fixed vector, right? So the answers are A and C, depending on the situation. Sliding vector is not a thing either. We don't have vectors that slide around. Yeah, that would be just a regular vector. All right, so here's the thing. I have I have this valve that is controlled by this giant wheel, right? Why? Because it's awesome. That's why. Number one. A torque or a moment of 12 Newton meter is required to rotate this wheel. Why does one of the two grips of the wheel above require less force to rotate the wheel? Yes, it's the distance between them. The distance they are away creates this from the center, right? Creates a rotation, which is why if you want to do less work, you can turn this, right? So again, we'll go back to the door. It's really hard to open a door if you try to push it by the hinge. And you probably have all experienced this because I have, where sometimes you can't tell where the hinge is and you go to open the door and it's like like you can't open it because there's like you don't have enough force to get open because you're too close to the rotational point, right? Yeah, sure. Just run as fast as you can into the door every time. All right, but yeah, so there's this intuitive concept, right, that you can generate more force the further you are away, or sorry, you can generate more torque for the same amount of force by placing those two forces further away if you're trying to get a rotation, right? And I think that's pretty intuitive, and you guys have probably experienced this a number of times. But let's say you drove a really old vehicle, right? Uh, back before the days of power steering. Okay? Or maybe you have a really sweet truck, and then the power steering goes out, because sometimes that happens too, right? Your power steering is just like, hey, that's cool. I'm going to take the day off, right? So in older vehicles without power steering, how big of a wheel do you need to be able to turn the vehicle well, right? That's why in a lot of older vehicles you'll see large steering wheels, because it takes less force for you to have to produce that rotation, because there's no assistive mechanism from your power steering. Okay, great. So that's why couples are important, right? There's real life applications to couples. But one of the things that's really great about the moment of a couple of forces, and notice it's the moment of a couple, right? It means two forces, two. No more, no less. Two there always are. Okay? Master and apprentice. A couple is defined as two parallel forces with the same magnitude but opposite direction, separated by a perpendicular distance. Like there, right? So we've got our blue potato up here, and I've got a force coming this way and one going this way. These forces are parallel to one another. They are both called force F and negative F to indicate to us that they have the same magnitude in opposite directions, right? And they are separated by this different distance r, which happens to be perpendicular to both of these vectors, right? And that's great. So what does that mean? It means the moment of a couple is defined as MO is equal to F times D if we're using a scalar analysis, or M about point O is R cross F if we're using a vector. This is R. R is the distance between the two forces. It is not the distance from O in this case, right? Notice that R is up here. It's the difference, it's the distance between. That's what makes this different than when we're defining a traditional moment. Because if we were doing this for each of the forces, we would take the distance from O. We care about the distance that they are separated when we are dealing with a couple. Okay? We're dealing with a couple. Okay, great. Right-hand rule still applies. Right-hand rule still applies. So in this case, if this is the distance r between my two forces and I'm pushing on the ends, you'll see that you should get an even rotation if the forces are in fact equal and opposite. So r is any position vector from the line of action of f to negative f. And I know that says from f to f, and that doesn't make any sense because you can't have a line from one thing to itself. I guess you could be like, you could go around, right? But this distance r. Anyway. All right. The net external effect of a couple is that the net force equals 0, and the magnitude of the net moment equals F times D. And it is a free vector in most cases, but there are certain cases where this would be fixed. For most top part, we are going to consider this a free vector, meaning that I can just put it wherever. I can put this moment wherever I want. Wherever I want. It's great. We made this couple. We put it wherever we want. Where should we put it? It doesn't really matter. It's free vector. Free vectors for everybody today. Look under your chair. You get a vector, and you get a vector. You all get vectors. It's Dr. D's favorite thing day. All right. Since the moment of a couple depends only on the distance between the forces, the moment of the couple is a free vector, and it can be moved anywhere on the body and have the same external effect on the body. Moments due to couples can be added together the same way that we add any vectors together. So you have two different couples, and you want to get the net moment between those two different couples. You would get the x, y, and z components, and you would just add all of those together, right? And then you would get the resultant moment, right? Because it's a vector. I know it's weird because it looks like we draw it like a spinning, we draw it as a rotation, but remember, it's just a vector, right? Okay, so let's actually do one. right? So here I've got this problem of this beam. And you can see that I've got a couple of different forces acting on this beam, or a couple of forces, right? I have two couples with this geometry. And the magnitude of F, I need to find the magnitude of F so that the resultant couple moment is 1.5 kilonewton meters clockwise, right? Great. That sounds fun. Let's try this. Try this out. So where are we going to start here? Well, we're going to start with redrawing our free body diagram. All right, so I'm going to get a fresh page here, and we'll just do this. Right, so this is going to be a very complex free body diagram, as you will see. There it is. Perfect. Just the way that I wanted it. Feel really good about it. We're going to have a force here. That's F. We also have another force over here that I'm going to call negative F. I know. Genius, really. We also have a force here. That's 2 kilonewton. And a force down here. It's also 2 kilonewton, but in the opposite direction. We were given the thickness of the beam, so I guess I'll actually draw that part real quick. Perfect. Just how we wanted it, right? This is the thickness of the beam is 0.3 meters, and the distance between F and negative F was given as 0.9 meters. There's our free body diagram. One thing that we're missing, and I would have lost points for, my coordinate axes. And this time the rotation sense is on there for us to remind us that we are going to have positive rotations in the counterclockwise direction. Okay. What do we know? Things that we were told. The resultant moment is 1.5 kilonewton meters, but it is in the clockwise direction, negative. Is that going to be I, J, or K, do you guys think? Should be about the K axis, right? Why? How do we know that? Because this is a 2D problem, so we don't really have a choice. We don't have to work. For 2D problems, your rotations will always be about the axis coming in or out of the board, right? For 2D problems. Great. What are we asked to find? We're going to find the magnitude of F. Okay. Really what this is asking us is to simplify the forces that we have acting on this beam into a single moment, right? That is what the whole point of this is. When we look at this, we see that we have two different sets of couples, and we were just talking about that. So I can create a moment for each of these sets of forces, right? So let's start there. We'll start with the 2 kilonewton force, right? The moment of the 2 kilonewton couple. Well, that's going to be 2 kilonewtons times 0.3 meters. Right? And this is a scalar approach that we're doing right now, right? Which gives us 0.6 kilonewton meter. Why are we doing this scalar instead of the vector approach? Because it's easier to do this as a scalar. Okay, that's great. What were we told? We were told what the sense of the final resultant moment is going to be. If we're looking at this moment right now, the 2 kilonewton one, right? Say we wanted to assign directionality to it right now, because we kind of do, just for our own edification, right? If I was to push and pull this, right, in this direction, so let's say this is the edge of my beam, and I have a 2 kilonewton force going this way and another one coming towards me. What direction does this go in? Counterclockwise, which makes it a positive moment. So this should be this direction. Right? I would make note of it, or I would say CCW for counterclockwise, however you want to note it, right? But remember, this is a scalar, so we need to track it ourselves as to what the direction is. Does that necessarily matter at the end of the day? Yes and no, and we'll see why in a second, okay? Mostly yes, keep track of it. If I wanted the moment from the force F, well, that should be the magnitude of F times 0.9 meters, right? Well, that's cool. Is that one going to be positive or negative? I have my beam back, right? One goes up. Negative, right? If I push up on that end and down, it would cause a rotation that goes in the clockwise direction, right? I'm going to track this one as negative. I can't really do anything else with that, so we leave it, right? Why? Because we know that the resultant has to equal the moment from the 2 kilonewton plus the moment due to F. But we're also given the resultant moment, right? Okay. We can solve this for F. And if we do that, we will see that the force needed to create this specific resultant moment is 2.33, the magnitude of it. In this case, we don't care about the direction because we know one has to be positive and one has to be negative. And given what we've done, we were just asked for the magnitude, so it doesn't really matter, right? But we know it's a couple, and so each of them has to have the same magnitude, right? So it's 2.33 kilonewton. Right. Again, why is that helpful? I would argue that if you were designing for a specific moment loading, you know how much force you need to apply or what the maximum amount of force is I can apply before I exceed that in this case, right? So I don't know, I guess whatever is attached to those ropes, make it less than 2.33 kilonewton. Otherwise, something might happen. Yeah. Yeah, I mean, if you have 2.33 kilonewton ropes, bigger issues that we need to talk about. At the gym, if you're doing your ropes with 2000 Newton ropes, I would recommend checking out World's Strongest Man. That's what I would recommend. If you can do ropes with 8,000 pounds, almost 9,000 pounds, then I would like to see that. Please post a video in the Discord. All right. Any questions on this? So it seems trivial, right? I know it seems trivial. Seems like a trivial example, but this is a really powerful thing, right? Because if I had given you the force, you could have told me what I can get rid of all those forces and just write them as a moment, right? And so now I've decluttered entire free body diagram. Instead of having 4 forces, I just have to worry about one quantity being on there, right? Which makes it pretty powerful when we have really complex systems that we can identify couples, and now we can remove forces from there and just say, hey, the net effect of this force is this rotation, right? All right, let's do another one. Is there a picture for this? There. For some reason, I animated that one because that's great. Okay, this one is a little bit different, right? So I have a 450 Newton force, and it's a couple acting on this pipe assembly. And the couple moment in Cartesian vector notation is what we are after. So this one, last one was a scalar, right? This one we need to be a, this one we need to be done in the vector quantity, right? So where do we start? Well, we'll start by redrawing our free body diagram here. Why? Because it's what we like to draw free body diagrams to get lots of practice doing free body diagrams because they're the best and they're going to ensure that Professor Bullock doesn't yell at us when we get to MEE 352. For that, at least. Might yell at you for something else. And then it ensures that he won't yell at me later, which is really, isn't that the most important thing? All right, anyway. Rid of that guy. All right. So now we got to put on our, oh, 0.4 meters. We've got some origin point down here. That's Y, Z, X. We know that these are both 3, 4, 5 triangles. We'll call this F sub A because that's what it's called in the picture. You can't see it. The other one's called F sub B. I'm going to call them both F sub A. Why? Because they're a couple, and we know that they're a couple. So it doesn't really matter, frankly. All right, let's write down the things that we know. The magnitude of FA is equal to the magnitude of FB is equal to 450 Newton. That's most of what we know, right? We also have distances. I'm not going to write down all the distances, but I will say, hey, we know distances. You're good. What are we looking to find, or what are our unknowns? Well, in this case, we were asked specifically to find the moment of the force couple. I'm just going to call this one M because it's a free vector. And if I put a subscript on it, that's going to indicate to people that that's supposed to be somewhere. And it's not. It's just the moment of the system, right? So again, remember, you can put it wherever you like, right? Because it's a free vector. Great. So what do we have to do here? Well, okay, equation of a moment, as we saw many, many times, and then I put in the boxes, right, is this. It's R cross F. Now, because it's the moment of a couple, it's the distance between the forces now, right? So let's find R. If I'm going to find R, I need to go essentially from A to B, which is why RAB is on there. I'm just going to call it R, right? Because I'm going to go fast and loose on this one. That's why. Crazy. Renegade. Okay, so what's the X component? 0.4. 0.4 in the eye. And unless my eyes deceive me, that's it. Now, you could also do this by finding ROA and ROB and subtracting the two. But you know what that's going to leave you with? The one that we got. So there you go. Great. Now we need to find that force vector. Okay. I'm going to hope that I did this correctly this time and don't have stuff on the next slide. Excellent. I'll move this up here. All right, let's find the force vector. How are we going to do that? F is equal to what? Specifically, we'll call it, we're going to say that it's F, doesn't really matter. We'll use FB. Okay, why are we going to use FB instead of FA? It matters in the sense of the direction, right? Well, so why would you use one over the other? Why do you think? Why would I choose FB instead of FA here? It's not more positives, no. Where did we define our position vector from and to? That's RAB, right? But I just put it as R. So it went from A to B. So where it terminates is the one that we are going to choose as our force vector. You could have used RBA and then used the force at A, right? But wherever it terminates, right? So we remember, right? I will write it as RAB. Terminates at B, right? So let's draw the vector between, uh-oh, that's not what I want. No, 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 no. RAB, right there. So nice. Okay, so if we want FB, right, and remember these are essentially mirror images of one another. They have the same magnitude. How do I get the X component of this force at B? What's the X component of my force? Yeah, 0, right? Should, hopefully, it doesn't look like it's going, looks like it's in plane, 0I. What about J? Positive or negative? Positive 4/5 times 450, which is the magnitude of the force that we were given, force B. What about the Z direction? Negative 3/5 times 450. I will put the unit vectors there because you have to. Otherwise, then you just add them all together and then you get a mess. All right, so we've got our force vector. This is going to be really nice, right? And why do I say that? Because we have so many zeros in our position vector that there's going to be a ton of things that just cancel out here when we take the cross product, right? There's going to be a ton of things. So we'll do the cross product out. The moment is equal to ijk of 0.400, 0. 4/5 of 450 is 360. Sorry, minus on the last one, minus 270 in the K. Using minus 270. Get my special cross product tools ready. Boom. There we go. Yeah, feel free. 0I. Whoop. Sorry. Switched up on me. What? No, no. Want. 0I. Does everybody see and agree with me that that's 0I? Yep. Guess what? Minus 0J. Why did you put the minus? Because of the direction. Just to be consistent with my directions. Does it matter? Does not matter. If you wrote plus 0J. Oh, sorry. My bad. No, that's what I said. Minus 0.4 times negative 270 minus 0. That's what I said, guys. In the J. Nope, K not 0. Plus 0.4 times 360 minus 0 in the K. Is everybody comfortable with the directionalities that we've given I, J, and K here? Does that make sense? I know it keeps repeating. I keep repeating myself. It's important. It's important for the bookkeeping that we get it, right? I, J, and K in the directions, right? So I cross the I, if you cover the I column, right? You're left with J cross K. J cross K gives you positive I. If you cover the J column, you have I cross K. I cross K is the reverse right-hand rule or the left-hand rule, right? It goes against the right-hand rule, so that makes it negative. It's going to be positive here anyway, if you can't tell, because there's a negative inside of that quantity, and so negative minus a negative should be a positive. And then K, for the same reason, when we cover up K, we're left with I cross J. I cross J gives us positive K due to the right-hand rule, right? And so we get positive K. We do this all out, and we get that our moment is equal to 0I plus 108J plus 144K. And that's the couple. And so now if we wanted to redraw our free body diagram, which we don't have to, but if we wanted to, we could get rid of these forces, right? It wasn't asked for us to do this, but I'm going to do it anyway. Right? I can get rid of these forces, get rid of my position there. And I can just draw this as a moment about the X, Y, and Z axis. Well, there's nothing about the X. It's positive 108 around the Y, right? And so if we're looking here, this is positive, this is positive, that's positive, just to keep track of it. So about the Y axis, we have 108. That's our moment in the Y direction. Positive. Right? And about the Z axis, our, about the Z axis, we would also have a positive Z. Okay. So now we can replace those forces with those moment components. Could you draw a vector in 3 dimensions to show the rotation of the J? Good luck with that. I wish you the best. I am not good at drawing a rotation that would look like that. You can draw it that way. You will see that some people will use this notation, right? Where we know that it's a JK, so it's going to be in the YZ plane. They'll do that. And you can find the angle for that, right? If you wanted to. You just use the tangent of the Z over the Y, right? You can find it. But most people will just draw it as a vector, and they'll make it special by putting a rotation like around it so that you know it's a moment vector and not just a regular plain old force vector. Okay. But the thing that's important is now, instead of all of these things, we could put that anywhere, right? We can put it at the origin. It might make more sense. I don't know. Come on. Take this vector and I'll like put it on the bar somewhere, right? You can put it wherever you want. It's a free vector. It doesn't matter. The net effect is going to be the same. Okay. All right. Let's talk about, let's do this one. You guys, where are we at? Okay. A little bit of time left. Good. F1 and F2 form a couple. The moment of the couple is given by which one of the A, B, C, or D? R1 times R1 cross F1, R2 cross F1, F2 cross R1, and R2 cross F2. Which one of these is how we would define the couple? B's, some B's, some B's in the back. We need some A's, B's, B's. Answer is, well, we got mostly B's. Nope, no answer for you. No, all right. The answer is B. Why? Why is it B? There you go. Because R2 terminates at F1, right? You were pointing, so that's a fancy way, right, of saying that one vector points at that force. Okay, right? I said it as terminates. Just think of it, this is going to be much easier. If the vector points at the force, that's what you want. You want the vector to point at the force. Okay. This one is the opposite direction. That's not going to give you a moment. That's going to give you some other quantity that's negative of your moment. So I guess technically, if you really wanted to, you could say, you do that and go negative with it, but I wouldn't recommend. This one's B. All right. If three couples act on a body, the overall result is that the net force is not equal to zero. The net force and net moment are equal to zero. The net moment equals zero, but the net force is not necessarily equal to zero. And the net force equals zero, but the net moment is not necessarily equal to zero. Man, it's a lot of words. So three couples act on a body. So there's three of them. So six forces. Presumably we can couple them up all together. The overall result, what's the net effect on whatever this object is? Is the net effect that the net force is not equal to zero? Let's assume this system's in static equilibrium since this is a statics class. Okay. The net force and the net moment are equal to zero. The net moment equals zero, but the net force is not necessarily equal to zero. Or D, the net force equals zero, but the net moment is not necessarily equal to zero. Okay. Looks like D's and C's way around. Answer here is D. Because remember what it's doing, right? The net force is going to be zero, but net rotation, the moment might not be, right? The forces are still statically in equilibrium. Okay. We don't have time for you to do this problem right now. Would have been lovely. Let's talk about how we would start this problem since we have some time. Okay. So what are we told? We've got two couples acting on this beam. That's not really a beam, it's a frame. I don't know why this says beam. It's wrong. With a geometry shown, and the distance between the two forces is 4 feet. And we want to find the resultant couple. Now, they say the resultant couple. That means the moment. They want to find the moment. right? The couple moment. So, all right, so what we have? We've got two sets of forces. Cool. We want to find MR, the resultant moment. Much more realistic than when we were given a resultant moment, and well, not more realistic. It's more intuitive how we were going to do this, right? So what's our plan? First, we're going to resolve the forces into X and Y directions so we can treat them as couples. Well, can't I just treat them as couples as is? You sure? Sure, you could. But they're at different angles, right? And so in the last problem, it worked out pretty nicely because we had two for one couple that was a 3-4-5 triangle, right? And so then we found the distance between them and we just did our, I mean, we still needed to find the X and Y components, right? In order to do the cross product. So it's not like it's going to save us anything to just say, okay, well, we'll do this vector wise, right? So let's just take a look at it and we'll see. Okay, what happens? What happens if we break these down? Okay. What happens if we break these down? What's the X component? Let's start with the 30 degrees one. If I wanted the X component for the 50 pounds at 30 degrees, what would that be? Right. I mean, so here's the other thing, right? The other reason why I would recommend this, right, is based on the information that you have, right? If a moment, well, let's write the equation down, right? Let's write the equation down. I'm going to back it up for a second. If the moment is equal to R cross F, right? Yeah. And R for a couple is the distance between those two that is also perpendicular to both of those. What's R? Is that perpendicular, the perpendicular distance between those? How would you find R? You got to recreate your coordinate axes and do some trig, which is maybe not where you want to be. But if we were to break this into X and Y components, I want to show you something. Let's break this into X and Y components, right? So, yeah, that's a big arrow. And we'll do the other one too. Okay. And I will actually, oh, no, I'll actually do this correctly, maybe. Let's use the mouse. I'm gonna move that up there. I'm gonna move this down here. Okay, if you draw these in components, something very interesting happens. What is it? Well, the X components for the 30-pound force both go through themselves. There's no moment created by those. The couple moment generated by those two forces is zero because they share a line of action. The distance away from each other is zero, right? Same thing with the Y component from below. So we end up being able to simplify this problem and get two moments that have zero magnitude, right? Why? Because remember, they pass through each other. Now, could you have spent the time to figure out like that distance? Well, more realistically, this distance. Sure, right? You know that the angle is 30 degrees, so that should be 30 degrees off of the horizontal right? And you know that that makes that bottom leg of the triangle 3 feet. So you could figure out that distance. It's not a big deal. And you could do this at the vector, right? You could make a vector in Cartesian and say from whatever we'll call that to wherever it is, right? And you can do the same thing here, right? You can figure out, 3, 4, 5 triangle and the distance between these two vectors, right? You can do that, right? But breaking it down into X and Y components allows us to simplify it just a little bit, right? We'll actually do this problem. We'll go through the entire thing. Next class. It's just we don't have enough time to do it, right? So then what do we do when we're done with this? We find all the moments due to these couples, and we add them together, right? And we move on. Yeah, Colin. Yes. Yes, that's what I'm saying. So specifically the moments due to those. Specifically the moments. Okay. There were a lot of examples in this one. We'll keep moving where we left off next class. It's a good thing we were a little bit ahead. Over there.
Oh, I know that this is 30, so then, you know what they call it? I've been trying to look them up. Like, where I'm from, we learned it like really early in school. So
Sure.
they're like, because this angle is like, there's like complementary stuff.
So there's like complementary angles, there's interior angles. I would look up, if you want to learn more about it, I would look into like, oh man, I'm blanking on the name now. Shoot.
And that's because it's really, that's been the most difficult thing for me to like make that connection. This angle is this, then you should automatically know that.
Sure. And I think look into complementary angles. Start there, and that should probably bring up a lot of stuff. Yep. Oh, okay. Free car. Hey, what's up? Good question. When, yeah, take these kind. When are you leaving? This Saturday? Coming up? Okay. So it's gonna have to be either Thursday or Friday this week. Um, Probably Friday, I gotta contact the test center, because you're gonna have to reach out to them to go take it with them. Let me reach out and see, and we'll get it set up. All right, yep.
Too much, but she also gonna be here for Thursday. For
Yes.
the test. Okay. So would it be just same as her contract?
So when are you leaving?
I think Wednesday.
Next week on Wednesday?
Wednesday afternoon.
So, right. Yeah, I'll contact the test center. Send me a message in Halo, so I don't forget.
Okay.
Yeah. Mm. Okay.
setup that I got. It's
Sure.
just
I mean, that's a little much. I'm more concerned about references in the IEEE style.
like
So
the-
don't worry about like your, yeah, so like, yeah, this
So you-
stuff.
like,
Yeah,
and then there's the references
Yeah.
according to
yes. No problem.
So I understand everything, but then I just have one question for like these problems. If you use like for this or
Yeah.
this, like how would you know when to like use that for like
Sure.
which ones?
So if we're going after the Y component here, right, because that's the base one, right?
Yeah.
So if I wanted so normally if we had an angle, right, we would say, well, that's the cosine, right?
Yeah.
But in this case, let's see,
I have another problem with, actually on other problems, where like you use the difference between cosine and sine.
Sure.
I'm noticing that like on matrix, like.
So in this case, right, if I have this vector like this, right, and we can see that that's in the ZY plane, right?
Yeah.
So if we were to look at it straight like this, in a typical situation, we might have this thing, right? And if that's theta, right, we know that sine is equal to opposite over hypotenuse, adjacent over hypotenuse, and tangent is opposite over adjacent, right? So this is our y component and this is our z component here, right? So in this case, we would want the cosine to get the y component because that's the adjacent side. But we know for this that this is a 3, 4, 5 triangle. So that if the cosine is the adjacent over the hypotenuse, then that's where the 4/5 comes in. Because that's just the adjacent side over the hypotenuse. And that's equivalent to the cosine of whatever theta is.
Okay, so then I understand that.
Yeah.
Now I'm still a little confused on what you meant by like how you found for sure that that's cosine. Like, how would you know by this angle that it's like for sure cosine? And because like of the
Mhm.
arrow, like when you put like the
So wherever this angle is where we're concerned about, right? And so the adjacent side to this angle, not counting the hypotenuse, would always be, if I want the cosine, that's going to give me that. Because what's going to happen, right? So let's say I don't know this. I don't know the y component here, right? So anyway. Right? This is equal to the cosine of theta if I knew the angle, right? So if I wanted to solve for y, I would have to do the magnitude of the hypotenuse times the cosine of that angle, right? And so that's where that comes from. Um, if it's, I would recommend starting here, right, and looking at these things, right? So like, what do you know? Typically, in all these cases, we tend to know what this hypotenuse is, right? We know the magnitude. In this case, it was F, whatever, 450 newtons, right?
yeah.
So we know the hypotenuse. If I'm looking, in that case, right, if I'm looking for the opposite side, that would be FZ. So FZ over F has to be equal to the sine of whatever that angle is. We didn't have the angle, we had this. We had a similar triangle. But the angle between here on a similar triangle is the same, right? And so that's why we know we can take, well, 3/5 here, because in the similar triangle, the sine of this angle here is 3/5. And that's where the 3/5 comes from, right? And so then FZ would be 3/5 times the magnitude of the hypotenuse,
Okay,
right?
that makes more sense.
Yeah, so I would say start with this, see what you know. And if you calculate all of them, it doesn't really matter, but I would definitely start with that.
Okay. So I should just always like write down like the SOHCAHTOA stuff.
Yeah.
Okay.
I think if you find it helpful as a reminder, for sure. Right. Absolutely.
Thank you. I appreciate it.
Yeah, no problem.